Okay, in section 15.4, we're going to talk about impact. And impact occurs when bodies collide. We have two types of impact. Central impact, which occurs when a body with a velocity is moving along a line of action, and this body A then strikes another body B, moving also in the line of action, or could be stationary, or could be moving slower than A, but both are moving with the velocity in the line of impact here. So we call this the line of impact. This line of impact goes through the center of mass of these bodies, and we can define another line perpendicular here, which is the line or plane of impact. So that is central impact. Another form of impact is oblique. And oblique impact occurs when one or both bodies are approaching from an oblique angle, and the line of impact is still the same and goes through the center of mass. Let's do this in red. Line of impact. And the same with the plane of impact. But we see here that this VA approaches at an angle theta, and this VB, although I wrote VA down here, this VB approaches at in general at a different angle of phi, or it possibly is approaching or stationary on the line of impact. So let's talk about central impact first. So let's say we have two objects moving along a line, and the momentum of the first object is MAVA, and the momentum of the second object is MBVB. And in this example here, B will be moving slower than A so that they contact each other. If B was moving faster than A, they would never impact. So this is the sort of situation that occurs. So A and B impact, and deformation starts to occur. This results in a deformation impulse. Let's say that this is our positive direction here for our little situation that's occurring, and at the point of contact, and we have then a minus deformation impulse here, and these two cancel out as deformation begins to occur. Notice in this case, velocity of A and B are still somewhat different. Eventually the maximum deformation occurs, and A and B now have a common velocity, V, as the two are hooked together. A restitution period now occurs as A and B begin to move apart, and changes the impulse. We'll represent it here by positive and negative R dt. Notice that the P dt is greater than the R dt due to losses. Finally, A and B separate again. Now with a different velocity from before. And at this point, the velocity B is a little greater than the velocity of A, allowing the separation. And up here, velocity A is greater than the velocity of B. So over this process, momentum is conserved since the two impulses cancel fully, and we still use the momentum equation, conservation of momentum equation, where our initial momentums equal our final momentums Now, since we typically have the velocity of A at the beginning and the velocity of B at the beginning, in order to find the other two unknowns in this equation, we're going to need another equation. And so what we'll do is look at the individual momentums of the particles. So during the deformation period, we have mass of A times the velocity of A at 1 minus the integral of P dt. So again, we'll count this as positive, and I'm looking up here at this area for my deformation period. And this equals mass times the acceleration, or mass of A, not mass times acceleration, times the velocity, times a velocity that's occurring at this time. And then in the restitution phase, we're going to end up with ma velocity minus the r dt equals ma velocity of A at 2. I'm going to define something called the coefficient of restitution, E, and I'll define it as the integral of r dt here over the integral of P dt. So what we end up with then is V minus the velocity of A at 2 divided by the velocity of A at 1 minus V. Now I can do the same thing, same idea here for B. So these would be the impulse momentum equations for B. Then coming up with restitution, where I would take again the integral of r dt over the integral of P dt. This is going to equal. And I would have this relationship. Now, comparing both E's, we see that we have these V values in here, and these V values are the same for each particle A and particle B. So I can eliminate these, solve simultaneously, and eliminate the V's, and rewrite this equation as E equals the velocity of B final minus the velocity of A final over your initial A velocity minus your initial B velocity. And this, in combination with conservation of momentum, will be used to solve problems. Two equations with two unknowns. So the coefficient of restitution can be described as the relative velocity after the impact divided by the relative velocity before the impact. And when you have E equals 1, you have a completely elastic impact. So no energy is lost. And when you have E equals 0, you have a fully plastic impact, and the two particles merge. Anything in between those is a combination of both. And so for the central impact, impact occurs along the line of impact, and the resulting velocities also occur along the line of this impact. So let's look at our oblique impact now. So we have impacts coming in general from two different directions at velocity 1 and theta 1 for particle A, and velocity of B initially with a initial angle from B. When after impact, we'll have then some angle phi2, and of course this will be at some velocity b2. Let's put this one here and one here, and this will be at some velocity a2 with a theta 2. So let's look at the impulse momentum for particle A. So we have particle A. Let's split this up into Cartesian directions here. So we have mass times the velocity of A in the x direction initially, and then we'll have in general some velocity, mass times some velocity in the A y direction initially, and to this we'll add an impact impulse, integral f dt. This is then going to result in our A particle with different momentum in, well, it's actually going to end up with the same momentum in the y direction, we'll see, but we're going to see that in a second. But with momentum in the y direction and different momentum in the x direction in general, m a v a x 2. So if we look in the x direction with positive defined to the right, we end up with mass of A times the velocity of A in the x direction initially minus an impulse equals mass times the velocity of AX in the x direction final, and this all occurs along the line of impact. In the y direction, we don't have an impulse, so we end up with this relationship, and this leads to the relationship that just the velocity of A initial equals the velocity of A final. And here's for B. So momentum is conserved along the line of impact, the x-axis, and we will have two equations to use in that on that axis. And then perpendicular to the line of action, usually in the y direction, if the x-axis is along the line of impact, we will have this relationship where mass times velocity initially equals mass times velocity in the final situation. The masses divide out, and you get the velocity of your initial velocity equals your final velocity in both cases.